So we're now moving into section 2.6, and we're going to talk about related rates word problems. This is going to be an application of implicit differentiation, and in any class of mine when I do word problems, rather than like doing notes normally and making you copy down the word problems and stuff, I think it's easier to use packets for those things. So that's what we're going to take a look at. We're going to take a look at the packet that you should all have titled Related Rate Problems. And the first thing I'd like you to do is take a moment, flip to page 2. One of these years I'm going to renumber things, but I want to start with problem number 2. I'd like you to take a moment and just read problem number 2. So before we start getting into how we're going to go about solving this, I'd like to try to convince you that the radius and the area are changing at different rates. Let me get out my notepad for this one. Let me think. Let me make a column over here for our time. Over here we're going to say the radius. Over here I'm going to say my area. Let's assume at time t equals 1 second, the radius is 1 foot, which means my area is going to be, we know that the area of a circle is pi r squared. So my area is going to be pi times 1 squared, or just pi. And area would be feet squared. Because we know the radius is increasing at a rate of 1 foot per second, I know after 2 seconds my radius is going to be 2 feet, giving me an area of pi times 2 squared, or 4 pi feet squared. When t equals 3 seconds, my radius is 3 feet. My area is going to be pi times 3 squared, or 9 pi feet squared. When t equals 4 seconds, my radius is 4 feet. My area is pi times 4 squared, or 16 pi feet squared. I think this is good enough to see that the radius is increasing at a constant rate, 1 foot, 2 feet, 3 feet, 4 feet, but the area is not. Pi feet squared to 4 pi feet squared, so that's an increase of 3 pi. Then I have an increase of 5 pi, then an increase of 7 pi. Even though the radius was increasing at a constant rate, the area is not. The area is increasing at an increasing rate, 3 pi, 5 pi, 7 pi, and so on. Then, I don't really care about finding the rate of increase over an interval. So between like time 1 second and 2 seconds, my area will have increased 3 pi feet squared per 1 second. But that's an average rate of change. I want to find the instantaneous rate of change right when, I guess in this problem, right when the radius happens to be 4 feet. So hopefully this chart gave us an idea of what's going on, how the radius and area are changing at different rates, but this is not how we're going to go about actually solving any of these problems. Here's what we're going to do. And there is a 4-step process we're going to use to solve all of these problems. Going back to the first page. The first thing we're going to do is we're going to tell what is always true. Maybe a formula that always holds, a rate that is a constant rate, things that are not changing. Maybe a value that's not changing. In part 2, I'm going to try to figure out what exactly this problem is looking for me to find in general and at a specific instant. We'll see what that means in a moment. Part 3 is when we're going to go do some calculus. We're going to find a derivative, and somehow it's going to be an implicit derivative. I'll make a formula for the rate I'm looking for. And then in part 4, I'll deal with my specific instant. Here's how we're going to apply these steps. Oops, notepad again. Okay. Step number 1. Let's see, what is always true here? Well, I know that the area of the circle is always going to be A equals pi times r squared. That's something that is always true. Now, the kind of different part of this is the radius and the area are actually both functions of time. The radius is different at different times. The area is different at different times. So even though I've got a equals pi r squared, what I'm really dealing with in this problem is a of t equals pi times r of t squared. Everything is a function of time. Next, we're told that the radius is increasing at a constant rate of 1 foot per second. Well, derivatives are rates of change. What this means is the derivative of my radius is a constant 1 foot per second. I know that the derivative, r prime of t, is always going to equal that constant 1 foot per second. Now, this is probably the easier way to think about it, but the symbol I'm going to use instead of r prime of t is I'm going to use dr dt equals 1 foot per second. I know that my area is always pi times r squared. And really, I know my area, which is a function of time, is always pi times my radius, which is a function of time, squared. And I know that the derivative of the radius, the rate of change of the radius, is always 1 foot per second. The second thing we're going to look for, I want to figure out what I'm actually asked for in this problem. When the radius is 4 feet, at what rate is the total area changing? I want to find the rate of change of the area. If r prime of t is the rate of change of the area, is the rate of change of the radius, the rate of change of the area is a prime of t. I want to find a prime of t. Using our other notation, this is really like finding dA dt. I want to do this, in general, find a formula for dA dt, the rate of change of the area, but specifically when I'm done, I want to deal with the instant when the radius happens to equal 4 feet. So when I'm done, I want to deal with this when the radius equals 4 feet. I'm going to put that in a little dashed box over here to say that when I'm done, this is what I'm going to deal with. Please just stick with me through this. This is one of those things where you have to see an entire problem done out, and it'll make a little bit of sense by the time we're done. But then we'll do another one and another and another, and by the time we finish this video, you should have a clue of how this whole process is working. So I know this is complicated and confusing. Stick with me. I promise we'll be okay. The third thing I'm going to do is try to create my formula for a prime of t. Create my formula for the derivative of this thing. Well, I'm going to go and I'm going to do my derivative. I want to find the derivative with respect to time, because everything is a function of time, of a of t equals pi times r of t squared. The derivative of a of t is a prime of t. On the other side, I have pi times the derivative of r of t squared. That's going to require me to use the chain rule. This is going to be 2 times r of t times, well, the derivative of this thing. By the chain rule, we've got to multiply by the derivative of the inside, and the derivative of r of t is r prime of t. Now, the problem with this is our notation, it just gets very cumbersome. Instead of always showing area is a function of time and radius is a function of time and all those things, I'm going to instead simplify this and just look at the formula a equals pi r squared. I'm not writing that a and r are both functions of time, but it's implied, which means the derivative of a is going to be dA dt, same thing as a prime of t. The derivative of the other part is pi times derivative of r squared is going to be 2r times the derivative of r, because r is really a function of time, dr dt. These have the exact same meaning, but this is a little bit less cumbersome to write out, and this is really the notation we're going to be using for our related rates problems. There's one other thing, though, that I'm going to go do in this step. I was told in the initial setup of this problem that the radius is always increasing at a rate of 1 foot per second. I'm going to go plug in that 1 foot per second for dr dt because that is something that is always true. That is something that is not changing. I'm going to make a formula, dA dt equals 2 pi r times 1, or dA dt equals 2 pi r. This is my formula for the rate of change of the area. Now, I need to, in part 4, deal with my specific instant. I wanted to find the rate of change of the area at the instant when the radius happened to be 4 feet. That was what I said over here. I couldn't plug in the 4 earlier because, well, the radius, that's something that's changing. Anything that's changing has to be represented by a variable. But now that I'm done and I've created my formula for dA dt, I'm going to plug in my 4. And I'm going to say that dA dt equals 2 times pi times 4, and I'm going to get 8 pi. There's one final thing that I have to figure out. I have to figure out the units for this. dA dt, the derivative of a with respect to time, the derivative of area with respect to time, well, the units for area are feet squared, because radius was given in feet. The units for time are in seconds, so my units are going to be feet squared per second, really just the units for area over the units for time. If the radius is increasing at a constant rate of 1 foot per second, when the radius happens to be 4 feet, the rate of change of my area is 8 pi feet squared per second. Again, I know this is very complicated. Please stick with me. We're going to be all right. I would like you to take a moment and read through problem number 1, and I'm going to make the video pause. Air is blown into a spherical bubble. Well, a spherical bubble is another way of saying a sphere. I am not dealing with area here. I'm dealing with volume. Partially, I know that because of my units over here, cubic centimeters per second. So I need a formula for the volume of a sphere. There's an easy way to find this. It involves looking at the cover of your packet. You will not have to memorize the volume of a sphere. That formula will be given anytime we need it. But I'm told that the volume of a sphere is 4/3 pi r cubed. So that's going to be the formula that I start with. V equals 4/3 pi r cubed. The volume is always 4/3 pi r cubed. I'm not going to show my v of t, my r of t. It's just going to be implied that these are functions of t. Next, I am told that air is being blown into a spherical bubble at this rate. I need to figure out what this is the rate of change of. Is this the rate of change of the radius, dr dt, or is it the rate of change of the volume, dv dt? And I feel like the units might help you out here. Cubic centimeters per second, this is the rate of change of the volume. I'm going to say that dv dt, the rate of change of my volume, equals 10 cubic centimeters per second. And I think that's all that is constant. The volume is always this formula over here, and the rate of change of the volume is always 10 cubic centimeters per second. Step 2. I need to figure out what I'm looking for. I want to find the rate that the radius is changing. Okay, so I want to find dr dt. And I want to find this in particular when the radius happens to be 1 centimeter. And this is my setup. Part 3, I'm going to go and do my derivative. What's the derivative of v? dv dt. On the other side, I have that constant I'm just going to leave out front, 4/3 pi. The derivative of r cubed, should be 3r squared, but by the chain rule, we've got to multiply that by what? I hope you just said dr dt. I can clean this formula up a little bit, and I can say dv dt equals 4 pi r squared dr dt. And I'm going to fill in the rate that I'm given that is not changing. I'm going to go fill in my dv dt, which is 10 cubic centimeters per second. So I'm going to say 10 equals 4 pi r squared dr dt. I don't need to solve for dr dt. I don't need to make a dr dt equals formula. I'm just going to leave it like this, and that's going to be fine. Sorry, my phone keeps buzzing, and it's shaking the table. So that's what you're hearing if you're hearing random noises. Okay, now we need to deal with our specific instance. I'd like you to plug in 1 for r, solve to get dr dt, and see if you can put units on it. See what you can get for that. I'm going to say that 10 equals 4 pi times 1 squared dr dt. 10 over 4 pi equals dr dt. Can clean that up to dr dt equals 5 over 2 pi. Make sure that pi is in your denominator. Then, as for the units, r is the radius. Well, the radius is measured in centimeters. T is the time. It's measured in seconds. At what rate is this increasing? 5 over 2 pi centimeters per second. I'm going to pause here, so if you're still making notes, finish writing things down, and then we'll look at 2 more examples in this video. Okay, so take a moment. Read number 3. This one's going to be a little different. How fast does the water level drop when a cylindrical tank of radius 6 is drained at a rate of 3 cubic feet per minute? Okay, first of all, we need the formula for the volume of a cylinder. V equals pi r squared times h. Now, water is drained at a rate of 3 cubic feet per minute. First question for you. What is that going to be? dv dt, the rate of change of the volume, dr dt, the rate of change of the radius, or dh dt, the rate of change of the height? Well, I'm going to use the units to help me out a little bit. The units are cubic feet per minute. That's a volume thing. Plus, we're removing water. We're removing the stuff inside. It will affect the radius and height, sort of. But this is a dv dt. I know that dv dt equals 3 feet cubed per minute. Next question for you. If water is being drained, should this dv dt be positive or be negative? Is the volume of water inside that tank increasing or decreasing? Because the volume of water in the tank is decreasing, I'm going to make my dv dt negative 3 cubic feet per minute. Part 2. How fast does the water level drop? Is that referring to dr dt or dh dt? The water level is related to the height of the water in the cylinder, so I want to find dh dt. In particular when, oh wait a minute, I don't have a particular height here. They tell me that the radius is 6 feet, but this is kind of interesting. If we think about water draining from this tank, I've got water in here, wonderful, water's leaving and all that stuff. As the water's draining, the height's changing, but the radius of the water is not changing. The radius is always going to be 6 because this is a cylinder. So actually, because the radius is not changing, I can plug that in part 1. I'm going to say my radius equals 6 feet is something that is not changing. So V is going to equal pi times 6 squared times h. My formula is going to be 36 pi h. And that's the formula I'm really going to use. Part 3. We need to go do the derivative. By the way, I know I didn't give you a specific instant in part 2. We're actually going to see it's not going to matter. We need to go do the derivative of this thing. Take a moment, see if you can get your dv dt equals formula. The derivative of v is dv dt. On the other side, that's 36 pi times the derivative of h is dh dt. I know my dv dt is -3. So I'm going to fill that in. And actually, because there's no specific instant, I can solve right now for dh dt. And what this just means is the height is always going to be changing at the rate that I'm about to find. I can get dh dt equals -3 over 36 pi. I'll simplify that to -1 over 12 pi. And this is in, okay, h is the height, that's going to be feet. T is the time, that's measured in minutes. So -1 over 12 pi feet per minute. Because the radius of the water, think about it again, you've got water in this tank. As water's draining, the height of the water, that's definitely changing. But the radius itself will always, not the radius, the water itself will always form a little cylinder with a radius of 6. That's not changing. Its height is, but the radius isn't, which is why I was able to plug 6 in the beginning. Anything changing needs to be a variable, but anything not changing can be just filled in right away. And I think that's all I have to say about that. One more example we're going to look at in this video. Take a moment, read through problem 4. In this problem, we have some magic cylinder where both the radius and the height are changing. So here we go. V equals pi r squared h. I don't have a radius that is constant nor a height that's constant. These two things are part of my specific instant that I'll fill in part 2. But I do have dr dt, and I also have dh dt. dr dt is the rate of change of the radius, and I know the radius is decreasing at a rate of 4 feet per minute. I'm going to say dr dt equals negative, because it's decreasing, 4 feet per minute. dh dt, the rate of change of the height, is 2 feet per minute. See if you can set up part 2, where we try to figure out what we're looking for and the specific instant when we want to deal with it. I want to find the rate of change of the volume. I want to find dv dt. In particular, when the radius is 2 and the height is 6 at that particular instant. When the radius equals 2 feet and the height equals 6 feet. I'm going to go put that in my box. Part 3, I need to do my derivative, and we've got to be a little bit careful over here. The derivative of v, dv dt, equals pi times. If I want to do the derivative of this product over here of two variables, I have to use my product rule. r squared times h, I need to do my first times derivative of the second plus second times derivative of the first. First is r squared. What are we going to say the derivative of h is? I hope you just said dh dt. plus second, which is h, times derivative of the first. Derivative of r squared is going to be 2r, but by the chain rule times the derivative of r, which is what? dr dt. That's my calculus step. I'm now going to go and I'm going to plug in my rates that are not changing. My dh dt is always 2. My dr dt is always -4. dv dt is going to equal, you take a moment, go plug those in and just kind of clean that up a little bit. Let's see, minus 8 hr or something like that. Part 4, we're going to deal with our specific instant. I'd like you to plug in your 2 for r, your 6 for h. Get an answer. Yes, it's perfectly okay if you want to use the calculator for this. But let's try to get an exact answer that has a pi in it. And stick some units on your answer. See what you can do. Minus 48 times 2 is 96. I'm thinking negative 88 pi. This is volume, so I'm going to say cubic feet per, the units for time are minutes, cubic feet per minute. Does this mean when the radius is 2 feet and the height is 6 feet, so both of those things are changing, is the volume itself increasing or is it decreasing? Yeah, it should be decreasing because that dv dt, that rate of change in the volume, was something negative. I hope that after watching this video, you feel like you have a little bit of a clue with these related rates things. It's going to take some time before we feel a little bit more comfortable with this, which is why we're going to be spending 3 or 4 days on more of these word problems. I promise you, please trust me, by the time we're done with all of the days of this, you will feel comfortable about this and you will be fine come our test on this stuff. It's just going to take a little while.